This is Geometry Semester 1. It's the 5th unit called Pythagorean Theorem. It's the second lesson within that unit called Perfect Squares, Simplifying Radicals, Rationalizing Denominators, Practice. It's on creatormath.com under the Geometry tab. You might have to Google creatormath.weebly.com to find the site. The instructions are copy the following problems into your composition book on the correct pages according to the table of contents with the notes for those pages from creatormath.com. So before we jump into the problems, let's try to show you where the notes are and how to find them and where to put them in your comp book. So here's the website. It's creatormath.weebly.com. Google that. Hopefully you can get to the home page. It looks like this. Scroll down and you'll see all the instructions on how to do your composition book to get 100% on that. Watch all the videos, follow all the deadlines, and follow all the instructions. We're going to go straight to geometry. That's where all the notes, videos, vocabulary, and problem sets are. All right, so this right here, the Vocabulary Geometry Practice Study PDF, this is a PDF of all of the vocabulary for the entire year. If you're not getting 100% on your vocabulary practices, please find that PDF and Google how to search it. We're going to find the right semester. Please focus on which one you're in and find the right one. We're in the lesson from semester 1 here, and we're looking at Geometry Table of Contents. This should have been written on pages 2 through 6 of your composition book already. If not, stop what you're doing and write it in. Please follow the video on how to number the pages of your comp book so that you get that right. We're going to move down to this unit, which is right here, Pythagorean Theorem. That's the unit. And then we're in lesson 2, Perfect Squares, Simplifying Radicals, Rationalizing Denominators. Here are the page numbers it goes in your comp book. Please don't look at this video for the page numbers, but go back to the original table of contents like I'm doing. By the time you watch this, these numbers will probably be different. The notes are here, the problems here, and this video solution will be linked right here. So we're going to click Notes. Fair warning, sometimes I have to load it twice. Nope, loaded the first time that time. So what are we talking about? We're talking about perfect squares and square roots, right? What's a perfect square? Well, if you take 1 and square it, you get 1, 2 and square it, you get 4, 3 and square it, you get 9. Of course, to the power 2 means to multiply this base by itself that many times. So 3 squared is 3 times 3, or 9. 4 squared is 4 times 4, or 16. The reverse of a power 2 is a 2 root, otherwise known as a square root. Maybe that's hard to see. So say we have 4 squared equals 16. The way to go backwards, math always has a forward, a power, and then a root is backwards. So if we take the root of 16, we'll go back to 4. These are perfect squares because they're integer values. In other words, if you took the square root of 17, it's going to be a messy decimal. But if you take the square root of 16, you get a 4. And that's why it's called a perfect square and square root. All right, because you're dealing with integer values and not with decimals or irrational numbers or those kind of things. All right, so this lesson is going to take us through a problem set on this. We're also going to figure out how to simplify radicals. We'll show you that in a minute. You're looking for what perfect square is buried inside of this 12. It's going to be a 4 because 4 is a perfect square root. And we'll pull that out, show you that in a minute. There's cubes here too. Fair warning, I don't use cubes that often, but I try to get my students to memorize up to 1 through 10 cubed. Honestly, I don't know how much I use them, and here is some simplifying of cubed roots. We might look back at this in the problem set. Let's see how many of those they give us. Rationalizing the denominator, another huge topic as part of this lesson. We are not allowed to have a radical or square root in the denominator position of a fraction. So if our answer is 2 over square root of 3, we have to do this thing called rationalizing. We multiply this by square root of 3 over square root of 3. Why did we pick square root of 3? Because that matches the denominator. Once we multiply square root of 3 times square root of 3, we get square root of 9, and that disappears and becomes 3. Notice this final answer does not have a radical in the denominator position. We're allowed to have one in the numerator. That's fine. So we're going to do a few of those. We'll rationalize the denominator. Again, topics for students that are a part of other problems this lesson is about, but can really mess you up if you don't sort of have an understanding of them. So let's roll through these problems, and if for some reason we run out of time, Let's see how our time's doing. Then students can log off if we get to the end of the period before we're done with this. So what is the Pythagorean theorem? So you should know this from the prior lesson. We expect you to use height squared equals leg squared plus leg squared. That's the very best way to do it. If you just say a squared plus b squared equals c squared, you kind of know half of it. But I have no idea if you understand that c has got to be the hypotenuse. So I'd like you to do it this way, all right? What is the hypotenuse in a right triangle? More than one answer may apply. The hypotenuse, by now, you should know, is the longest side, and it's the side across from the 90-degree angle. The side at the bottom, no. The shortest side, no. The side across from the smallest angle, no. Two answers apply here. And I'm going a little bit fast because I remember these from the first lesson in this unit. What is the leg in a right triangle? So either of the two sides touching the right angle, true. Is it the longest side? No. Is it the side across from the largest angle? No. That's the hypotenuse, not the legs. All right, so, and just to give a quick reference drawing, in a right triangle, if this is the 90, because I drew a square here, this is a leg, and this is the height. Okay, the hypotenuse. The two legs are touching or attached to the right angle. A triangle has two legs, like a human. The legs touch the 90. The hypotenuse does not. It's across from the 90. It's the longest side and the side across from the largest angle. So, what is the square root of 1? Just so you know, this is the way the computer writes a square root symbol. It is kind of like this, and that's it. And they put a 1 here. They want to know the square root of 1, like this. We use 1, 2, 3, 4, 5 different pieces of our square root symbol if we write it. The square root of 1 is 1, you guys. It's what number times itself equals the number under the square root symbol. 1 times 1 is 1, so it's got to be 1. What's the square root of 4? Square root of 4 has got to be 2, because 2 times 2 equals 4. Right? It looks like I got a lot of problems here, so I'm going to move pretty quickly through these. What's the square root of 9? 3, because 3 times 3 equals 9. Square root of 16 is 4, because 4 times 4 is 16. Square root of 25, 5. Because 5 times 5 is 25. And notice these are all perfect squares and square roots because they're integer values. There's no decimals involved here. What's square root of 36? 6. Square root of 49? 7. Square root of 64? 8. Square root of 81? 9. Because 9 times 9 is 81. And looks like they're going to keep rolling here. Square root of 100? 10. Square root of 121, 11. Square root of 144, 12. Interestingly enough, students learn 12 times 12 early on. I'm not sure what's sticky about that, but a lot of students know 12 squared is 144, and the square root of 144 is 12. Square root of 169 is 13. Square root of 196 is 14. Square root of 225 is 15. And I think you should memorize up to 20 or 25. You should probably have some grasp of. At least recognize it and go, 256 is a perfect square. That's 16 times 16. .289, the square root of 289 is 17. The square root of 324 is 18. And they're just going in order here, you guys. The square root of 361 is 19. The square root of 400 is 20. The square root of 441 is 21. The square root of 484 is 22. The square root of 529 is 23. I know that one less, but you can always use your calculator at some point with this, right? Just go ahead and type it in and say, what's the square root of 576? Maybe I can model that for you. If you go right here, let me say boom, boom, clear this. Remember, you're going to have to turn your calculator sideways to get the expanded calculator. So if you take square root of 576, right? 576, 24. Here we go. Square root of 625 is 25. What is 1 squared? Oh, I guess we're going to go in the other direction. 1 squared is 1. 1 times 1 is 1. 2 squared. Okay, 2 squared. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. And these are all perfect squares, and therefore they have perfect square roots. All right. 5 squared is 25. All right. Well, they gave us a lot of problems, but they're quick, I guess. 6 squared, 36. 7 squared, 49. 8 squared, 64. 9 squared, 81. 10 squared, 100. 11 squared, 121. 12 squared, 144. 13 squared is 169. 14 squared is 196. 15 squared is 225. Literally going in order up to 25, you guys. 16 squared is 256. 17 squared is 289. 18 squared is 324. And I do kind of forget these each year, and then I go back, I'm like, oh yeah, 324 is 18 squared. 361 is 19 squared. So it kind of depends on how familiar you are with the topic, and you can just sort of, this is a good warm-up, I guess, to get back into things. Not really a difficult assignment. 20 squared is 400. 21 squared is 441. 22 squared is 484. 23 squared is 529. 24 squared is 576. 25 squared is 625. All right, they're doing some cubed roots too. Probably, hopefully not up past 10, but cubed root of 1 is 1. You guys, because 1 times 1 times 1 is 1, right? So 1 cubed equals this. And the cubed root of 1 equals 1. That one's kind of cool, I guess. All right, cubed root of 8 is 2, because 2 times 2 is 4, times 2 again is 8. Cubed root of 27 is 3, because 3 times 3 is 9, times 3 again is 27. Cubed root of 64 is 4, because 4 times 4 is 16, times 4 again would be 64. Cubed root of 125 is 5, because 5 times 5 is 25, and 25 times 5 is 125. Cubed root of 216 is 6. Cubed root of 343 is 7. Cubed root of 512 is 8. And maybe they're going to give us 2 more. Cubed root of 729 is 9. Cubed root of 1,000 is 10, because 10 times 10 is 100, and 100 times 10 is 1,000. Now they're going the other direction. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. And these are most of all the cubes you're going to use in any geometry class, in any Pythagorean or any problem sets when we get into special rights and those kind of things. This covers everything. So 6 cubed is 216. 7 cubed is 343. 8 cubed is 512. 9 cubed is 729. 10 cubed is 1,000. So we went both directions, forward and reverse, with perfect squares and perfect cubes. So what's the first step in simplifying a radical? So what is the first step in simplifying a radical? I don't know if that's a good question here. This might be, how to simplify a radical, right? If it's an x squared and you're taking the square root, these reverse each other. Power 2 and 2 root are opposites. They disappear and you're left with x. Okay, what is the first step? I'm not sure if I like that question, right? But we want to do x cubed. So this is x squared times lifted to the power 2. It's going to be this one here, x squared. So it's the square root of x to the 6, right? Which has within it and I'm not sure I like that one right now. I might go back and revise that one, all right? I'm not sure I like these now that I look at them closer. What is the first step in simplifying the following radical? So we want to start to break this into pieces, and I appreciate this. This is probably a little bit better for this level we're on, right? If we can take 216 and break this into 4 times 9 times 6, now we can simplify and pull out the perfect square of of radical 4 is a 2, square root rather, and the perfect square root of 9 is a 3. We can pull those out front and simplify this. All right? And these two, they're going to start to break these down and divide these out. What is the square root of 216x to the 5th? So notice we have an x squared times an x squared would give us x to the 4th times an x. Good. So let's try this. We did this one on the last one. This is 4 times 9 times 6. That was 216. So that's helpful. Then we have x to the 5th here. We want all the x squareds we can put in this, right? We want x squared times x x. That will give us x to the 5th power here. Then y, we want the number of y squareds. So times y squared times y squared times y squared times y squared. Why are there 4 of them? Because it has to add up to 8. 2, 4, 6, 8. Right? Now when we take the square root of all this, each of these can be divided up into its own piece. So we can take square root of 4 times square root of 9 times square root of 6, etc. All right? And this is going to be square root of x squared times square root of x squared times square root of x. And now that I think about it, see, I would have rather they say this. This should be x squared times x squared times x squared and the square root of that. That's what I'd rather see here if it's x to the power 6. And then we can now say x squared square root, this equals x squared square root times x squared square root times x squared square root, all right? Which then comes out and goes x times x times x, which I would now say is x cubed. And that's what my brain is thinking. I don't like this one bit. I think this is x cubed right here. All right, so I'll go back and look at that and correct it by the time you get to it. All right, what is the first step? So I like this first step because it leads us down the path. Even though we're not experts at simplifying, we can get through these. So it's x cubed here, and the cubed root of an x cubed, these reverse each other. All right, so you're going to be left with just x. Fair enough. I like that one. This is going to be x cubed times x cubed and the cube root of this, which goes into the cubed root of x cubed times the cubed root of x cubed, which equals an x, because these reverse each other, times an x, because these reverse each other, which now equals x squared. I'm okay with this one. I'm all right with that answer. All right? And I don't like it that saying what's the first step. All this, I'm not sure they're really asking first step. These they are. These are good. What's the first step, right? Not sure that's the right question. So, 80. How about this one? We're trying to figure out what perfect cube is buried in 405. So the cubed root of 27 times 15. And the way this maps out is if we take 27 times 15, 27 times 15 equals 405. So this is legal, right? And what this equals is the cubed root of 27 times the cubed root of 15. Fair enough? This is the cubed root of 27, which is 3, times the cubed root of 15. All right, but they only want to take us to this first step right here. So this is what is the first step. I like that. What is the first step in this one? So now they're doing the same thing. Here's this. They're also breaking out this is x cubed times x cubed to get x to the 6. Y cubed would be one of these in here and y. All right, and the cubed root of all this. So this one can be, if this comes out later and you say the cubed root of y cubed, this is going to equal y, but this y will remain under the cubed root symbol in the next step. I wonder if they're going to make us go to the next step here. Maybe they are. All right, so this one is, what is the first step in rationalizing the denominator? So this is not bad because if you have a 2 over square root of 3, the first step is to multiply by square root of 3 over square root of 3. Why did we pick this to rationalize? So remember, here's what rationalizing is. We are not allowed to have a square root or a radical in the denominator of a fraction. It's against the rules in math. So to get rid of it, we multiply the whole thing by square root of 3 over square root of 3. Why did we pick square root of 3? Because that'll help us remove this square root of 3. Why is it square root of 3 over square root of 3? Because that equals 1. And you can multiply anything by 1, and it doesn't change the overall value. So now we multiply across the numerators, and we get 2 radical 3 on top. Denominators are radical 3 times radical 3, or radical 9. Radical 9 simplifies to 3, and you get 2 radical 3 over 3. This is the proper simplification of this. Okay? It's like having 2 over 6 as an answer, when really what you want is 1 over 3. This is the proper answer because it's reduced, even though both are the same value. These are both the same value. If you type them in your calculator, you'll see. But this is the acceptable answer because it's reduced. And I know it doesn't look reduced to students, so like it looks even more complicated than this, yes. But it doesn't have the radical in the denominator. All right. If you have 2 over radical 2 and you want to get rid of this down here, we're going to multiply by, so this one up here was radical 3 over 3. Now because it's a 2, it's radical 2 over 2. So radical 2 over radical 2 is what we'd multiply by. Check. What is the first step in rationalizing the denominator? If it were 3 over radical 4, guess what we're going to multiply it by? Radical 4 over radical 4. And they take it one last step. If you had 2 over radical 5, what would you multiply it by? Radical 5 over radical 5. And that's a 1. And you'd multiply through the top and the bottom. So it's going to be, I hope you're seeing the pattern. Whatever radical you're trying to get rid of in the denominator position, you multiply by the same thing over itself. All right, please match up the titles for these so that the problem set you're working on matches the video, your solution you're watching. This is Geometry, Semester 1. It's the 5th unit called Pythagorean Theorem. The 2nd lesson called Perfect Squares, Simplifying Radicals, Rationalizing Denominators Practice. It's on creatormath.com under the Geometry tab. Hope that helps.